Section 4.1, Exponential Functions. An exponential function is a function with the variable in the exponent. The base, b, has to be greater than 0 and not equal to 1. Let's look at an example. We have this exponential function which models the average amount spent in dollars at a shopping mall after X hours. And they want to know what is the average amount spent to the nearest dollar after 3 hours at the mall. So we'll take our function, and since it's 3 hours at the mall, X will be 3. So we'll find f of 3, and we will substitute that into our calculator, and it should work out to the value that you see here. And we round to the nearest whole number. So that tells us that after 3 hours at the mall, the average amount spent is $160. Example 2, we want to graph f of x equals 3 to the x. So we'll set up a table. I'm going to take them out of order because it's nice to start with f of 0. That gives us 3 to the 0, and anything to the 0 power is 1. It's also nice to find f of 1 because now we have 3 to the first power. 3 to the first power is 3. Next, we'll look at f of negative 1. Remember that negative exponents mean reciprocals, so this gives us the reciprocal of 3 to the first, which the reciprocal of 3 is 1/3. And our last point, 3 to the negative 2, that's the reciprocal of 3 squared. And so that's 1 over 3 squared, 1 over 9. We plot those points. Let's take a look. When x was 0, we're at a height of 1. When x was 1, we had a height of 3. At x equals negative 1, we're down at 1/3, so we just do our best to approximate that height. And finally, when we're back 2, we're up 1/9. We start getting really close to the x-axis, so it gets harder and harder for us to draw it. Note that it never touches, even though it will look like it on many of our graphs. Now let's look at some characteristics of exponential functions. The first one that we'll take a look at is domain and range. The domain are all the possible x values, and so if you consider the graph we just did, note that the x's can go back as far as negative infinity, and they will go to the right all the way to infinity. The range are the possible y values, and so note that that starts at 0 and continues up. When I say starts at 0, note that we use the parentheses here and not the hard bracket. A hard bracket would be used if it actually touched at 0, but it just starts barely above 0 and continues up towards positive infinity. The second thing we want to look at is that graphs of the form b to the x will pass through the point 0, 1. And this is because anything to the 0 power is 1. So that means that our y-intercept is always 1. So when we're thinking about y-intercepts, we have a y-intercept of 1, and the x-intercept, there's not going to be one, because as we said before, this comes close but does not touch the x-axis. The third characteristic we want to look at is that if b is greater than 1, then this graph will have an increasing value as it goes to the right. So as the x values get bigger, the y values will get bigger. Now we'll look at the fourth characteristic, which if b is between 0 and 1, then we'll have a decreasing function, which means as the x values get bigger, the y values get smaller. The fifth characteristic that we'll look at is that this function is one-to-one and has an inverse. Recall that a one-to-one function is a function in which no 2 points have the same y value. So if we have different x's, they'll be at different heights. And finally, we want to look at the idea of how this graph approaches but does not touch the x-axis. We call that a horizontal asymptote, and that simply means that this is coming down closer and closer to the x-axis, but it never touches. The equation of this asymptote would be the line y equals 0. Next, we're going to look at some transformations. So if we take our basic graph of b to the x, we can slide it around in various ways. So let's take a look. Vertical, the vertical transformation occurs if we add a constant to our b of x, then it's going to move it upwards c units. If we subtract a constant from our function, then it'll be a vertical shift downward c units. We can have horizontal shifts by adding to the exponent. If we add to the exponent, it will slide it left. If we subtract a value from the exponent, it will slide it right. We can have a reflection. If we multiply our function by a negative value, it'll be reflected about the x-axis. And if we multiply our exponent by a negative, it will be reflected about the y-axis. We have a couple more. We can have a vertical stretch or a vertical shrink if we multiply by a constant. So if that constant is greater than 1, we'll have a vertical stretch, and if that constant is between 0 and 1, we'll have a vertical shrink. We have horizontal stretches and shrinks by multiplying the exponent by a constant. It'll be a shrink if c is greater than 1, and it'll be a stretch if c is between 0 and 1. Let's take a look at an example. We want to use the graph that we did earlier of f of x equals 3 to the x, and we want to use a transformation to get the graph of 3 to the x minus 1. Here is our graph of f of x equals 3 to the x. We did this in example 2. These are 3 of the 4 points we looked at that time. Note that our new graph is 3 to the x minus 1. Recall that that gives us a horizontal shift. When you subtract from x, it's going to shift your graph to the right. So since we have a minus 1, it's going to shift our graph 1 unit to the right, and we can get that by adding 1 to each x coordinate. So the point 1, 3 in our old graph, by adding 1 to the x value, we get 2, 3. And the point 0, 1 becomes the point 1, 1. The point negative 1 comma 1/3 that we had on our original graph, when we add 1 to the x coordinate, we get 0 comma 1/3. And that is how you take your original graph and use a transformation. Note that we have a horizontal asymptote, and also note that they've graphed it using a dashed line. That is the standard practice because that line is important, but it's not part of the curve. Now let's look at the natural base e. You will not need to know this complicated definition for e, but you should take note that e is similar to pi in that it's an irrational number that goes on and on and on indefinitely. And it's an important number, so we'll ask that you memorize a couple decimal places, 2.72. But the good news is you probably won't need to use that, as most of the time we're using our calculator, and our calculator will give us many more digits of accuracy without memorizing. We call this the natural base because this base occurs naturally in various places like biology, finance, and even how long a light bulb will last before it burns out. If we have a function that involves e in this way, we call that the natural exponential function. In this example, we have a function that models the gray wolf population. We want to project the gray wolf population in 2014. 2014 is 36 years after 1978. You can always do that by doing a subtraction. So we'll substitute 36 into our function and find f of 36. That works out to be approximately 3,686. And so this indicates that the gray wolf population would be approximately 3,686 wolves in 2014. Now we can look at a couple formulas that we have for compound interest. The first one is for finding when there's compounding a certain number of times per year. We call those periods. So that formula, A is the future value, P is the principal that we have now, R is the interest rate written as a decimal. So for example, if it was 7%, we would put it in as 0.07. N in both places is the number of compounding periods per year, and T is the number of years. When there's continuous compounding, we use the natural base of E, and the other variables are the same as they were before. A is the future value, P is the current principal, R is the interest rate as a decimal, and T is the time in years. Let's take a look at this example. We have $10,000 of principal that we're investing at 1.08%. We want to find the balance in the account after 5 years. It's compounded quarterly. So if it's compounded quarterly, there's 4 quarters per year, so n equals 4. The formula that we use when it's got compounding is as shown here. We substitute the 10,000 in for the principal. We substitute the 1.08% in for the interest rate. Notice we move the decimal point 2 places to the left and we put it in as a decimal. The compounding was 4 times per year because it was quarterly, so both of the n's are 4, and the number of years is 5. And so the account balance after 5 years will be $10,554.08. Now let's look at example B. We have the same principal, the same interest rate, and the same length of time, but this time it's going to be continuous compounding. So we'll use our formula for continuous compounding, which is A equals P times e to the RT. We substitute in our values. Again, note that 1.08% we write as a decimal, so 0.0108, and we multiply that by the 5 up in the exponent. So the balance in the account after 5 years will be $10,554.85.